Hello and welcome to The Mystery of the Cylinder by Alex Heikert, Matthew Payne, Paul Van Keppel, and Neil Wolf. Today we'll be introducing fluid flow over a cylinder and then walking through the experiment we conducted to analyze this type of fluid flow. This will include what equipment was used, the procedure we followed, the methodology behind and analysis of the data collected, and a discussion about our results. External flow over a blunt body, such as a cylinder, will experience boundary layer separation, leading to wake flow oscillations. The viscosity of the fluid leads to the creation of a boundary layer. The boundary layer interacts with a change in pressure force exerted from the fluid. Some particles will reverse direction or completely stop, causing neighboring particles to separate from the cylinder. The pressure decreases along the front half of the cylinder, with maximum pressure at the stagnation point in the center. However, on the front half, the flow remains attached. In the back, there is a pressure increase where the flow can separate, creating highly turbulent regions called the wake. Vortices are shed by the wake, alternating the detaching location as seen in the diagram on the right. The frequency of the vortex shedding is a function of the Reynolds number. Vortex shedding causes an uneven pressure distribution on the top or bottom of the cylinder. The alternation of aerodynamic forces induces vibrations, especially if the resonant frequency of the cylinder is met. This was the case when wind gusts caused the Washington's Tacoma Narrows Bridge to collapse in 1940. For an overview of the experiment we conducted, we were testing a cylinder in the Cal Poly SLO low-speed wind tunnel as seen in the diagram at the bottom of the screen. Then we designed a test experiment that aimed to get meaningful data. The data was needed to compare experimental drag values to confirmed drag values and to analyze flow patterns at different Reynolds numbers. The goal of our analysis was to begin to understand the differences of flow over a cylinder both with and without a trip strip, calculate the coefficient of drag values for different scenarios, graph the effect a trip strip has on the coefficients of drag and pressure, visualize the characteristics of the created graphs by analyzing the FlowViz videos we recorded during testing, and finally compare how different sampling rate techniques affect the data.
The main piece of equipment used was the Cal Poly low-speed wind tunnel. Inside was the test rig, consisting of a hollow cylinder mounted horizontally in the tunnel, with 24 pressure taps drilled around its circumference in the center of the test section, each separated by 15 degrees. A Scanivalve mini pressure scanner was used to collect data from the 24 ports on the cylinder. To perform flow visualization, a 532 nanometer laser with a cylindrical lens was used to create a laser sheet in the vertical plane parallel to the flow. A fog machine with a PVC pipe distribution apparatus was used at the inlet to visualize flow in the test section. iPhone cameras were used to capture video and images of wakes and vortex shedding, and a boundary layer trip strip made of thin electrical wire was positioned on the cylinder using a Husky 9-inch digital level. The first step taken after securing the test rig in the tunnel and ensuring all lab equipment was prepared was to run through the lab safety checklist and startup procedure. Then, after taking wind-off data, we began our testing. With no trip strip, we recorded 2 sets of data at 200 RPM with an average per setting of 10, and then another 2 sets with an average per setting of 25. We then repeated these 4 data sets at 500 RPM. The wind tunnel was brought to a stop and the trip strips were applied using aluminum tape at 60 degrees above and below the horizontal on the front of the cylinder. The same tests were then repeated with the trip strips. At each stage, photos and videos were taken to document flow visualization, and after all the data had been collected, the tunnel was brought down to 100 and then 75 RPM to get better footage of vortex shedding. There were multiple sources of error to be considered for this lab. Due to a damaged test rig and punctured pressure lines, our first set of data was deemed unusable. The experiment was repeated to get reliable data. Additionally, the fog distribution apparatus slipped out of place on multiple occasions. Although this did not affect the pressure data, it did alter flow visualization images. Another error source to be reckoned with is the possibility that a trip strip could have shifted in the flow and covered up a pressure port, which could explain any outliers in our data. Lastly, due to the fact that there were two groups using the lab simultaneously, there is a possibility of accidental interference between the two separate testing procedures, settings, and conditions. Equations that were used in data analysis include the following for coefficient of drag, coefficient of pressure, and total drag force.
Added the trip strip for our 200 RPM test, we noticed that there was a significant difference in drag. The coefficient of drag was reduced from 1.15 to 0.9 by adding the trip strip, thereby reducing the drag force from 8.7 to 7.9 newtons. By using the theoretical equation, the coefficient of drag would only be 0.22, which would equate to a drag force of about 1.9 newtons. However, this theoretical cannot be reached due to flow separation. This graph shows the pressure values with the trip strip and without the trip strip while being compared to the theoretical for 200 RPMs. We proceeded to repeat the test at 500 RPMs again with and without the trip strip. The results were similar to what we gathered from the testing at 200 RPMs. The coefficient of drag was reduced from 1.10 to 0.95 by adding the trip strip, therefore reducing the overall drag force from 63 to 57 newtons. By using the theoretical drag coefficient, the drag would be 12.76 newtons. This graph shows the pressure values with the trip strip, without, and the theoretical for 500 RPMs. The next major part of the testing was to adjust the sampling rates. We changed the average setting from averaging 10 to 25 values to see how our data would be affected. The data itself was very similar at both sampling rates. The reason that they are slightly different is due to how the flow separates and the ability to capture these changes as pressure values. The graph shows 200 RPMs on the left side and 500 RPMs on the right side. Another way to compare our drag values was to take our 306 panel code and modify it to reflect the cylinder with 24 ports. The coefficient of drag from this code gave us a value of 0.25. This may be significantly different from our experimental values. However, it is fairly close to the theoretical coefficient of drag of 0.22. The graph on the left shows the modeled cylinder in a flow field, while the graph on the upper right shows the velocities on.
In order to better visualize the motion of air around the cylinder, we injected smoke into the test section, which was then illuminated by a 532 nanometer laser. The picture on the left shows a more separated flow and a large disturbed wake. The picture on the right shows the fluid staying attached longer, producing less wake and pressure drag at the same RPM. We took this video during our lab at very low RPMs in order to visually understand how a vortex sheds from a flow interrupting body. After repeating our data collection due to broken internal pressure taps, we got much better data the second time. After analyzing the effects of the trip strip, we determined that the trip strip actively reduces the pressure drag acting on the cylinder. At 200 RPMs, a CD drop of 0.25 was calculated, while at 500 RPMs, a drop of 0.15 was calculated. As seen in our flow visualization, the trip strip interrupts the natural reciprocating vortices, keeping the flow more uniformly attached to the cylinder. Comparing this graph found in the Lab 2 manual to the coefficient of pressure versus theta graph we produced during the test tells us that at 200 RPMs, the flow coming off the cylinder was mostly laminar. At 500 RPMs, we found the boundary layer was mostly turbulent. In conclusion, the experiment we ran determined that the trip strip attached had significant effects on the reduction of coefficient of pressure and drag. We supported this by using graphs of CP around the cylinder, a MATLAB panel code to calculate the pressure drag, and FlowViz to analyze the fluid behavior. We determined that if a lower CD is required, tripping the boundary layer to stay attached would be an effective way of lowering the value. Future tests and improvements on this experiment could be using a better camera, documenting pictures better with details, and testing the fluid effects of a sphere. Thank you for listening to our presentation on the effectiveness of a trip strip reducing pressure drag.